So the next two examples that we're going to give are a little bit more complicated or complex enthalpy change question that involve using the molar enthalpies of formation from pages 4 and 5 of our data booklet. So let's say I give you something like this where it asks you, what is the enthalpy change of reaction when 2 grams of methanol undergoes combustion in an open system? So one thing that we do want to kind of point out right away is that when we say open system, remember that open system when it comes to combustion reactions means that water vapor is produced. Okay? So H2O gas is produced. And that becomes important because it does have a slightly different molar enthalpy of formation value than water liquid. So what we're going to do is first write the balanced reaction, including all the appropriate states of the combustion of methanol in an open system. So writing the balanced reaction, we have 2 moles of methanol reacted with 3 moles of oxygen gas, which yields to 2 moles of carbon dioxide and 4 moles of water vapor. We're now going to resort to our data booklet and find all the molar enthalpies of formation for all the substances, keeping in mind that, remember, this is going to be 0 because it is an element. So using the molar enthalpies of formation enthalpy of reaction equation, we plug it in as follows. Remember that the coefficients here refer to the moles in the chemical equation. And we used water vapor value of negative 241.8 as opposed to water liquid. And when we tally that up, we get a total enthalpy change of reaction of a value negative 1275.8 kilojoules. So that's the amount of energy that's released when 2 moles of methanol are reacted. But what is it per 2 grams? So what we do is we write a proportion equation. We say that there is negative 1275.8 kilojoules per 2 moles of CH3OH. Then how many, so we're going to write delta H question mark, how many kilojoules are released when 2.0 grams of CH3OH are actually used? And so what we're going to have to do is isolate for this and convert this amount to moles. So quickly dividing the mass by the molar mass, we get 0.06242 moles of CH3. So again, plugging it back in, 1275.8 kilojoules. Let me just write that a little better. I apologize here. We're going to go 1275.8 kilojoules per 2 moles is equal to, again, we don't know this, but we're going to write delta H question mark per 0.06. Whoops, why is it not writing that? Let's try it again. 0.0642 moles of CH3OH. So what we're going to do is we're going to cross multiply this and then divide it by this, and that should give us the answer. And so the final answer when we cross multiply it and isolate for the new enthalpy change is negative 39.8 kilojoules. So this is a combination of the molar enthalpies of formation and proportions involved in thermal chemistry. The last example that we're going to do here is a chemical reaction is done below with molar enthalpies of reaction listed for each compound. Now these letters don't represent any compound necessarily, so it's just ideally. So we've got 2AB plus 3CD, which yields to 2CB plus 3AD plus 50 kilojoules. Now the fact that this is on the product side tells us that it's exothermic and that it's really negative 50 kilojoules, right? So let's say the first question is, what is the molar enthalpy of reaction of AD? And the molar enthalpy of reaction would be pretty straightforward in this case. Remember that the enthalpy of reaction is 50, And the molar enthalpy of reaction would just be the enthalpy of reaction, your delta H, divided by the number of moles in the reaction. And like we said before, the coefficients represent the number of moles in the reaction. So we have delta H divided by N is equal to the molar enthalpy, which is the Kj per mole. And in this case, it would be negative 50 over, and the amount of moles is 3. And when we plug that into our calculator, we get about, if this is a 3-digit answer, we're going to get about 16.7 kilojoules per mole. So when I ask for the molar enthalpies of reaction, you just take the enthalpy change and then you divide it by the number of moles. But remember that the reaction is different than the enthalpy of formation. What if I asked for the enthalpy of formation of AD? Well, when it comes to the enthalpy of formation, then we have to use delta H is equal to the sum of the enthalpy of the products minus the sum of the enthalpies of the reactants. And so there's a difference between the enthalpies of reaction and the enthalpies of formation. That would then yield to this equation where delta H is equal to the sum of the products minus the sum of the reactants. And then I would plug in each of these variables and then isolate for the one I'm looking for, which in our case is the molar enthalpy over here of AB. So plugging in all the values, you get something like this. And we would go back over here, we'd find that AB is 20 kilojoules. We're going to go, sorry, CB is, you know what, yeah, negative 10, so negative 10, and then plus 3. Actually, I said we wanted AB, but we actually wanted AD, not AB, my apologies. We actually want this one. So we're going to go 3AD, that's the one we don't know. And then we're going to go minus, and then 2 times the enthalpies of formation of AB, which is 2 times 20, and then plus 3 times, and we go to CD, and that'll be 10. And then what I find it's easiest to do is to actually do the multiplication that's simplified and then move everything over. So we would have negative 50 is equal to 2 times negative 10, gives us negative 20 plus 3AD, which is what we're trying to find, minus, and then we're going to go 2 times 20, which is equal to 40, plus 3 times 10, which is equal to 30, and then 40 plus 30 in total is going to be equal to 70, so minus 70. And then of course we can apply the brackets, and then we would have negative 50 equals, and I'm going to move this entire thing over here. This would become negative 70. When I move it over here, it becomes, and we'll do that right away, this would become, instead of negative 70, it'll become positive 70. And then it's equal to negative 20 plus 3AD. And then negative 50 plus 70 gives us 20 equals to negative 20 plus 3AD. And then we're going to bring the negative 20 over, which would become positive 20. And you'd have 20 plus 20 is equal to 3AD. And that would give us 40 is equal to 3AD. And then finally, we can divide both sides by 3. in order to get our molar enthalpies of formation of AD, and that would give us, when we put this in the calculator, if we're doing 3 digits, that would give us 13.3 kilojoules per mole, and that would equal the molar enthalpies of formation of AD, which is a different value than the molar enthalpies of reaction of AD. So, long story short, if we're asking for molar enthalpies of reaction, you want to use this equation. And if if you want to use molar enthalpies of formation, we want you to use this equation. If you're asked for molar enthalpies of reaction, you could simply just use this.